All right, so in this video, we're going to be looking at operations on functions, and we're going to be also looking at the domain in particular of these functions once you've done these operations on them. Now, we're going to start with two functions just as our example. So we're going to have f of x is equal to 4 minus x squared, and h of x is going to be the square root of 9 minus x. Now, the operations that you can perform on functions are going to include addition, subtraction, multiplication, division, and composition. So the addition, subtraction, multiplication ones do not tend to produce weird behavior in the domains. Wherever both of your functions are defined originally, where the domains overlap, the new function will behave exactly the same way. Where you will run into problems or changes in the domain is going to be potentially in the division and the composition cases. So let's walk through those a little bit because they can throw students off getting the correct answer. Now, another thing to kind of keep in mind about these operations is the function notation. So if I write an expression like this, f plus h of x, what I'm actually saying is calculate f of x plus h of x, put them together and as a single function. The x is not multiplying, it is part of the function notation. It's just saying what variable the function is written in terms of. So this sum would be 4 minus x squared plus the square root of 9 minus x. And that's it. The domain for this would be whatever the domain of that overlaps with both functions. This one is all real numbers. This one goes from negative infinity to 9. Negative infinity to 9. 9 is included because the square root can be 0. So as long as x is smaller than 9, it will be the square root will be defined because the value under it will be positive. Again, that's where they overlap. That's where both are true at the same time, and so that's the domain. Same thing for h minus f, for example. Again, that x is part of the notation. This means h of x minus f of x. And so then we would just, in this case, start with the square root. And then we would subtract our other function and make sure that we distribute to get our final answer, minus 4 plus x squared. What is the domain? Again, it's where they both overlap. And so that will be negative infinity to 9, since the polynomial is defined everywhere, and this is the one that has the only restriction. What about fg, or fh in this case? Now, occasionally you will see this expressed with a dot in between it. That is not to be confused with the composition notation, which is an open circle, but it's just multiplication. So again, not by x, but the two functions by each other. So f of x dot g of x is multiplication. Again, because of what x looks like, we rarely use the times with the x notation. It's either a dot or it's assumed. And of course, this is h. If we multiply them, 4 minus x squared times the square root of 9 minus x. And that's it. In some problems, if you have two polynomials, for example, there's value in distributing, but when you have two functions that don't really simplify, distributing doesn't really help, and so you can kind of leave it the way it is. And again, what happens to the domain? Nothing at all. Where are both functions defined? They're defined on the interval where the square root is defined in this example. Now, what about division? Let's do h divided by f. Again, this is h of x over f of x. So our numerator would be the square root, and then the denominator would be 4 minus x squared. Now, for the domain, one thing you have to keep in mind here is that the denominator cannot be 0. So even if both functions were thoroughly well defined, you cannot have a 0 denominator. And so those additional points will have to come out of the interval. And then wherever the numerator is defined, again, you have to combine the intervals so that you know where they're defined, but you have these new additional complications. So in this case, we would go from negative infinity. The denominator cannot be 2 or negative 2. If you set 4 minus x squared equal to 0, you get plus and minus 2 as your solutions. So it'll go to negative 2, and then we'll skip 2. We'll go from negative 2 to 2. We'll skip over 2, and then we'll go up to 9. Now, just as a side note, if I were to do the reverse, f over h, then what I would end up with is 4 minus x squared over the square root of 9 minus x. Now my new restriction is coming out of, again, is out of the denominator, but it's coming out of the square root. And the only point that would change is actually where the square root is equal to 0, which would be at 9. So I would not be able to include the 9 in my domain anymore. And then the last thing, the last operation that we can do is called composition. And again, this is represented with an open circle. And this means replacing inside your first function, your outside function, anywhere there's an x sticking in your inside function. So in this case, I would take 4 minus x squared. That's my template. That's my outside function. And then inside of this, I would stick in my radical, 9 minus x. Now, even though when I simplify this, I'm going to get the square and the square root is going to cancel. And so then I'm going to get 4 minus 9 plus x, which is going to give me x minus 5. Nonetheless, even though this is a linear equation in form, I still have to think about the domain being applied serially. So I can't stick a number into this function that I could not have stuck into either f or h. So in particular, my domain here is still going to be negative infinity to 9, because if I were to apply these in sequence, so first I pick a number and then I plug it into h, and then I get an answer, and then I plug that into f, which is what this is equivalent to. I can't plug in a number. If I can't plug the number into H, I can't get the result out of the final function. And so that restriction, even though it cancels in the algebra, nonetheless, that restriction on the domain remains.